Let's take a look at radicals. So a little bit of terminology first. The symbol, which may remind some of you a little bit of a long division symbol, is called the radical symbol. The number that appears under the radical symbol is called the radicand. So in this case, 9 is the radicand. On the second example, we have a radical symbol. The radicand is 8, and there's another number there which is called the index. Now, if the index is not written, it is 2. So because by far the most common radical has an index of 2, in other words a square root, we just leave it out. We don't bother writing it in. It's a little bit like not writing in an exponent of 1. It just is sort of assumed or not necessary. So let's see some examples of how you can use this. The square root of 9 is simply 3. It's the number that when you square it or multiply it by itself gives you 9. The cube root of 8 is 2. It's the number that when you cube it, in other words raise it to the power of 3, it gives you 8. Now, one thing to keep in mind is that the square root, the radical, is defined as the principal square root, which means only the positive square root. Because there is actually another number that when you square it gives you 9, and that is -3. So in fact there are 2 square roots, but if you use the radical symbol, you're only indicating the positive square root. So let's take a look at the examples below here. Square root 25, which is also sometimes just referred to as root 25, is 5, because 5 squared is 25. How about the cube root, or third root of 27? Now, if you're doing these things in your head, or they're giving you problems to do in your head, they're not going to be complicated, so the numbers are probably going to be pretty small. If you're not sure what the cube root of 27 is, just start trying things. 2 cubed, 2 times 2 times 2 is 8. That's too small. 3 cubed, 3 times 3 times 3 is indeed 27, and so the cube root of 27 is 3. How about the fourth root of 16? So it's a number that when you raise it to the 4th power gives you 16. Again, start small. Let's just start with 2. 2 to the power of 4 is 2 times 2 times 2 times 2. That's 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So the 4th root of 16 is 2. What if you have a fraction? Well, you can just simply apply the radical sign to the numerator and the denominator separately. So you would have root 9 over root 16. Now root 9, straightforward, that's 3. Root 16, straightforward, that's 4. And check it. Does 3 over 4 squared actually give you 9 over 16? Sure. 3 over 4 times 3 over 4 would give you 9 over 16. Same thing here. Cube root of 64 becomes our new numerator, and the cube root of 125 our new denominator. And it might take you a little while to come up with these numbers, but again, just start small. Start with 2, then go up to 3, 4, 5, etc. You'll find that 4 cubed is 64, so the cube root of 64 is 4. And 5 cubed is 125. 5 times 5 times 5, so the cube root of 125 is 5. Now, it certainly helps to know a few perfect squares and perfect cubes. A number is said to be a perfect square if you can take any rational number and square it and get it. So in other words, if I can take 1 and square it, I get 1. So 1 is a perfect square. 4 is a perfect square because it is 2 squared, and 2 is a rational number. 9 is a perfect square, etc., because 3 squared is 9. Perfect cubes. If you can take a rational number and cube it and get the number, it's a perfect cube. So for instance, 216, for instance, is 6 cubed. So it's straightforward to take the square root of a perfect square or the cube root of a perfect cube. But what if you take a square root of something that's not on this list? In other words, what if you take the square root of 2? Well, there is no rational number that when you square it gives you 2. And we saw this a little bit earlier when I introduced the concept of real numbers and talked about the 2 different sets, rational numbers and irrational numbers. This is irrational. And really what that means is there's nothing we can do to simplify this. You just simply have to write it as root 2. And it represents a number that is bigger than root 1, which is 1, but smaller than root 4, which is 2. So you can approximate root 2 quite easily as long as you know the perfect squares on either side of it. Similarly, let's take a look at, say, root 13. Okay, 13 is not a perfect square, so root 13 can't be simplified. This is irrational. But we do know something about root 13. It's got to be bigger than root 9, and we know that root 9 is 3, but smaller than root 16, and root 16 is 4. So root 13 is somewhere between 3 and 4, and this is often enough to answer a question. Let's try one for perfect cubes. So, for instance, let's say we had the cube root of 40. Well, this is also irrational. It can't be simplified because you can't write it as a rational number because 40 is not a perfect cube. But you do know that it's bigger than cube root of 27, so it's bigger than 3. It's smaller than the cube root of 64, so it's smaller than 4. It's somewhere between 3 and 4.